Alright, does this work? Yeah. Alright. Alright, let's see. It's been a long time. Well, not that long, but I did a bunch since the last time I recorded anything. So, yeah, I want to just walk over a bunch of the shit I worked on, because the main reason I do this is when I post the videos later, I can like have a record of what I was doing at the time, and it helps myself like remember what I was thinking about during that time. So, what have I done? So last time I made a video, I was working on the file system, and ultimately trying to get to a shell that can like navigate the like directories. So where I left off, I was trying to do like opening directories and reading them. You know, like on Linux you have opendir and readdir, right? Is it? Yeah, I think that's what it's called. So I want to implement something like that. Yo, what's up, dude? What's up? What's up? So yeah, let's go over what I did. So one of the main things I was missing was somebody to do dynamic memory like on the kernel side. So I had implemented malloc and user space, but if you wanted to have any dynamic memory in the kernel, all I had is a page allocator. So stream's fucked. We good? Alright. Hopefully it's good. Let me know if it's fucked again. So, yeah, I needed a kernel allocator. Like, so one thing I did is updated the page allocator so you can now like free pages. I just did a simple free list. Let's just open that up. So yeah, so now the first thing you do is you check a free list, which is just a linked list of pages. You got one that's free, give that one back. Or rather, you know, since alloc pages takes, oh, we're stuck again? Damn. Alright, wonder if that's on my end or on your end. I'm not seeing any drop frames here, but maybe I can just check it on mine. Let me see. Yeah, I can see the stream. Seems fine here. Maybe it's on your end. Let me know if it keeps fucking up. Maybe I'll reset or something, but I think it might be on your end. Alright. So the page allocator, you can allocate like a number of pages. So you, on the free list, it has its size. So like, do you have a free chunk of like n pages? If you do, you split that, you know, because you could have, say, 10 free pages. If you're asking for 5, split that into 5 now used, 5 free, give back that. Then otherwise just add a new, you know, allocate a new page. So that's one thing. Then the next thing was, all right, how do I get, you know, some resemblance of a memory allocator? So I looked into how Linux does things and found a good resource on a thing called a slab allocator. So here's a paper by Jeff Bonwick from Sun Microsystems. I think this is from like 1994, I think. Yeah, so the idea, the main idea here is that you have like it's like a pool kind of, you know how that works. The idea is to have like what they call a slab, which is just one or more pages of memory, and then you split that up into chunks of a certain size, and that's kind of like what a pool is, you know. An object pool is usually you have like a bunch of memory slots of the size of the object, and you can reuse those slots when one gets like freed. Um, so the idea of this slab allocator is like you kind of have like clients, so anyone in the kernel who wants to have like objects of a certain size, they can create a whole new slab. Um, I forget the terms they use for it. I changed them a little bit because throughout Linux and I guess Sun OS, because like that's where this is from, they use the term like kmem and kmem cache, and it's super confusing because when I think of a cache, I think of like, memory caching, but it's not that. They just use cache as a term for like a just like a chunk of memory, like an arena or something like that. But anyway, so uh, the other thing that this enables is a general like kmalloc, where you just say like, it mirrors like user space malloc, where you just say like, I want this many bytes, give me that back. So what it uses for that is internally the slab allocator actually on initialization creates a bunch of these like what I call them is slab pools, because I think of it as like similar to like an object pool. So like um, I call the main thing like a slab pool. So that's like a chunk of memory that's uh, divided into like objects of a certain size. That's a pool. So what it does is like takes base two, like uh, all your powers of two sizes, um, and makes slab pools for those. So for example, you can have objects of size 8 bytes, 16 bytes, 32 bytes, 64 bytes, up to 512 is what I do. Um, I just took that because this paper mentions like, where's the part about small? So I'll talk about this, but yeah, here, an eighth of a page. So since my pages are, 4 kilobytes, an eighth of a page is 512 bytes. So I use sizes 8 bytes up to 512 bytes in powers of 2. And so you create pools of that size, right? So if you say, and then when you call kmalloc, it just finds the closest size to that and allocates out of that pool. So, if you ask for 40 bytes, it'll round up to the next one, which is 64 bytes, and use the like 64 byte slab pool for that. Okay, so how do these things work? What they call a kmem slab, this is my slab pool, I guess. Or maybe this is what I call slab. I hate the difference in naming, but the idea is that like you have this thing that has a certain size. So this is for all, let's say 64 byte allocations will go in this one. And so you have these like metadata buffers that just tell you these act as like the free list basically, and have like metadata about the actual slot. But this is for the general use. For the size caches, which are like all those I was talking about from like 8 to 512, you actually use the buffer itself. So you don't have these like auxiliary data structures. It lives in the page itself. And so at the end of the page, you have like the slab structure. So I'll show you what they look like in code in a second. But so you have that at the end. The reason it's at the end is because they say like, in testing they found that the beginning is what gets touched the most. Where do they talk about that? Yeah, here. So the free list linkage resides at the end of the buffer rather than the beginning to facilitate debugging. This is driven by the empirical observation that the beginning of a data structure is typically more active than the end. Yeah. So that's this, but also at the end of each buffer, that's where this like buff control struct kind of lives, which in our case for these small objects, the only thing that's there is a pointer to the next free buffer. And you actually allocate a little bit of space for that. So like if the buffer is size 64 bytes, you add another 4 bytes for the pointer to the next, just for debugging help, because if like the buffer gets If there's a problem in the buffer, hopefully maybe that the pointer will still be there. Um, anyway, I don't know if I explained that well at all, but let's look at the slab. Alright, so here's like, this slab is what this is right here. So at the end of a page, and it is a page for sure because, you know, it's from sizes 8 bytes up to 512. If you have larger allocations, you could need more than one page, but for this, we're just using this basically to facilitate kmalloc, so that you can have, you know, a general purpose memory allocator in the kernel for small things, small allocations. Okay, so the slab at the end, what do you have? You just have a pointer to the free list, which is going to be like a pointer to the first buffer. So when you create a new one, it's a pointer to right here. That's the slab buff, which is just a linked list that has a pointer to the next one, right? And then the slab pool is like the parent of this, basically, because so for all 64-byte allocations, that's in the 64-byte slab pool, right? And so the slab pool could have multiple slabs because, you know, you could use up all of these buffers and need to allocate a new slab. So you would do that, and then this has a pointer to that next slab, right? Yeah, so that's kind of how that works. And then at that point, it kind of works like a regular like pool allocator. So like when you call kmalloc, it finds the closest size that it knows about, which in here, like I said, we have from 8 bytes up to 512. It finds the, you know, next closest size, and then looks for a buffer of that size in the free list. You know, so you're gonna go. This structure has the free list. You look for that for an empty slot. If you have one, you allocate it there. Remove this from this free slot. Otherwise, you have to grow. So you'll allocate a whole new slab, initialize it, and so on. So hopefully that makes some sense. That's how like the slab allocator works, basically. So yeah, here's kmalloc. Yep, just go through the slab pools, try to find one of that object size, and do that. And then freeing is cheap, you know, because it doesn't actually free the memory. All the freeing does is like add that buffer back to the free list. The other thing I should mention is like one of the main purposes for a slab allocator that we're not really utilizing it for. The impetus for Sun to do it is because they found that like they had a lot of objects that need to be initialized, you know, and that initialization could take a lot of work. And so with the slab pool, once it's initialized once, it doesn't get freed, so it stays in a valid, like, initialized state when you get a new one. So, you know, if it has, like, what are the examples they use? I think they had, like, it has, like, mutexes and conditional variables and stuff. Yeah, so, like, if this type of thing in there and initializing this is expensive, right, you don't have to destroy it and destroy the mutex and free the memory. All of it stays, like, as a valid initialized object in the slab. So when you get a new one, it avoids all of that computation, basically. But we're not really utilizing it for that. For us, we're just using it to facilitate basically kmalloc. Now, in the future, we can like, you know, extend it to fit whatever we need. For example, one of the things I've run into is having like a cache for directory entries. You want one of that specific size, because right now they're a little bit bigger than 256 bytes, so that means we have to bump up to 512, so I'm wasting like half the space on each one of those, but that's a digression. So, okay, that's slab allocators generally. Okay, the other allocator I made is just an arena allocator, and this one I didn't really read anything. I mean, you know, the main source for C folks that want to learn about arena allocator is this Ryan Fleury. I could pull up that resource really quick. Alright, so this right here is basically the Bible on arena allocators, so, you know, if you're interested in that, you can check that out. But you have to adapt that a little bit, because like the main idea behind that and why it's so powerful is because in a general, you know, when you're on user space side, you can utilize the virtual memory to great advantage with an arena allocator. You can reserve just a huge chunk of like address space, and then you know, you only pay for it when you touch it. But on the kernel side, you can't really do that. But I still wanted the convenience of an arena allocator. So I guess if you don't know what an arena allocator is, it's basically just you have a big old chunk of memory that you allocate up front, basically, and then I thought I had a image. Where's my arena? All right, well we can look at this. So ignore this in here and just say this is a big old chunk of memory. You allocate that up front, and you have the arena has a like pointer or like a cursor to where it is so far, and so whenever you allocate, you know, say I allocate 10 bytes, and then all it does is bump that up by 10 and return a pointer to where you were. And so the operations you could do is like allocating a certain amount, and you can pop the stack back to a previous point. So when you free, all it does is decrement a pointer, and when you allocate, all it does is increment a pointer. One consequence of this is like you don't get like intermingling freeze like you would with the general purpose malloc. Objects that live in this arena have a shared lifetime. So like, you know, you can allocate a bunch of stuff all at once and then free it all at once. But that's often you find what you want to do. That's generally kind of what an arena is. But in a kernel, it's a little more difficult because like you can't just allocate a big old chunk of like virtual memory up front. Or I guess, I mean, theoretically you could, but we're not really utilizing virtual memory in the kernel right now. So what I did is I came up with this idea. I mean, I don't know if it's a good idea, maybe it sucks, but this is what I was thinking. Basically, you the interface looks like this, right? You have get arena get. So what that does is you're gonna have just a global list of arenas that's in the kernel, right? And when you call get arena, it looks for one that's unused, and the first unused one it finds, it gives you that. If there's not an unused one, it allocates a brand new one and puts it on the list. The default size of an arena is 8 pages, and each time you get a new chunk, it gives you 8 pages at a time. And then these chunks, you can add on chunks whenever you need more memory. So say you're filling up this arena, you fill up all the data, you need a new one, it allocates a new chunk, and like adds a pointer in the end of this struct to this chunk. So that's arena get. When you need to like allocate from the arena, you call arena push, and that's what I was talking about, where like it just bumps a pointer and gives you back a pointer to where you started from. And then when you set the position back, that's basically like freeing. It just decrements the pointer. So the difficult part in this was just like, where do you store these like the arena struct and each chunk? Where do you store those? Because those take up memory too. And so the obvious answer for me was like, you store them in like the page itself that you've allocated. And I did it in the end to mirror what I had done in the slab allocator. And it has some pros and cons, but I like putting it there actually. The other problem I encountered is like, well, you need the arena struct, right, which has all of the metadata about the entire arena, you know, like its overall size, how many chunks it has in it, capacity, and all of that. But then when you get a new chunk, it's different, right? You have a different structure that's in the end of each chunk. And that introduces some complexity that I don't like. There's a number of ways you can fix that. I mean, one way you could just waste this extra space and always, use the size for arena. Boom, problem solved. The other thing you could do is store these externally. So like the metadata is not in these pages, it's elsewhere. But then where do you store that? I had the idea of, well, since we have a slab allocator now, you could store these in the slab allocator, but I just kind of wanted to have the simplicity of like a standalone arena. So I went with it this way. There's a little bit of complexity in like um, growing and shrinking the arena because of this. You basically have two cases you have to handle, and I don't like that, but it is what it is for right now. Okay, so what does it look like when you have to allocate? In the general case, it's very simple. You just increment a pointer and give that back. But the problem comes when you start crossing this boundary here. So like you're at the end of the data region in the arena, there's a number of cases, right? It could be that this is how big the arena is. It's only 8 pages, and you've run out of those, like that memory, so you have to allocate a new chunk. In that case, well, you have to allocate some pages. You have to call the page allocator to get a new chunk, set it up, and then give a pointer to the beginning of this chunk, right? But it also could be that you already have more chunks that have been allocated, but it's just been decremented since then. So from there, you'd have to find the next chunk and give the pointer back to the beginning. And the same thing happens like when you are like freeing, just like setting the position back to a previous point. Because let's say you are right here and you're setting it way back to here, you just have to handle the multiple cases that you could have. I don't know how worth it is going into detail on that. C-Films, what's up? How you doing? I'm alright, I'm tired. And, but I'm good, alright, I'm good. I feel like I'm just forever tired now. I'm just an old man. Alright, that's enough detail, I think. That's kind of how the arena allocator works. It's pretty simple. The only like complexity is in like managing where do you store these like metadata structs. I just store them in here, and you have two, so you have a different, like the first allocation is a different case, special case that you have to handle. Hell yeah, glad you're doing great, homie. Interpreter or compiler? Not here. Is the title still wrong? This is a little operating system. I never know it. Does my title say compiler still? Because I was working on a compiler before. But this is a little operating system. Yeah. So, okay, that's the arena allocator. What else do I want to talk about? So, one of the reasons I was doing those is to facilitate having an open system call. Okay, that's the title. Yeah, that's right. Thank you. Okay. Yeah, so the next thing I did was like a open syscall. So for like a step back to a larger perspective, the thing I wanted to do is have like a shell that can navigate the file system. And so there's a lot of things I needed to facilitate that. One of the first ones is like, all right, the commands you're gonna want generally. So operating systems are not compiled. I mean, it is, but I'm not writing the compiler for that. Like I'm just writing it in C, so I just use a C compiler. This operating system is for a RISC-V, like 32-bit CPU. So I use Clang to compile to that target. Yep. I mean, here, look. This is the build script. This is how I build the operating system. Right now, like the only usable in program is the shell. So, I compile that separately to like object file. building the file system is an external thing. I just have a utility that does that. And so the kernel is basically the operating system, right? So I just call clang on that because like CC is clang. So you just compile it to 32-bit RISC-V, and then this runs in a virtual machine. So I'm not running it on actual hardware. I use QEMU. That's the way most people develop an operating system because it's way easier. Yeah. So what was I talking about? What was I talking about? Yeah, so the main sort of commands you want in a shell for navigating a file system, right, is like, you know, what's my current directory? I need a command to change directories and like list what's in this directory. So that's the high level goal of like, you know, the absolute basics things you need in an operating system is that. So to facilitate that, one of the things you need to do is like, well, you need to like, first of all, list, you need some notion of a working directory, right? I'm just trying to figure out like which order to talk about in this, because I mean, you can look at, like, these are all the things that I had done since like last time. So what order do we talk about? I mean, an open syscall is a good place to start, right? So let's look at that. Or maybe we start in userland and look at like how the shell calls it, right? Actually, no. We're gonna start with like open. All right. So like this is the user space interface. It's like a wrapper around the syscall, right? So when you call open, you give it a path to the file in the file system, some flags, you know, whether it's read or write, and whether it's a directory or not, and a mode, which I'm not using that. This is for like when you're creating a file. I'm basically copying how Linux does things to start with because it's like easy to find information on that, and I'm just building this to learn anyway. There's places where I diverge because I'm just trying my own thing, but in general, I'm copying what Linux does a lot of the time because I'm just trying to learn how, you know, an operating system works. So, you know, this mirrors how Linux Open works. You give it a path, some flags, and a mode. Alright, so this calls into the kernel via a syscall. So let's look at the syscalls. When you get open, what does it need to do, right? Well, you have to like walk basically the directory, like the path that you're given, like the sub components of that path, looking for each subdirectory until you get to the actual file you're looking for. So this introduces another concept of like caching directory entries. I'll talk about that too, but at the high level, what you have to do is like, let's say you're trying to open like code hello.c, right? So when you initialize the file system, you create a root, like, there's two things you do. You initialize the inode table. So the inode is basically like the actual identity of a file, and it holds all the metadata about it, but it doesn't actually store like the path, because in Linux you can have like symlinks and all sorts of things, so it doesn't have a canonical name really, or at least not a unique one. And so, you know, you have an inode table which has all the metadata about files and like where they actually live on the file system, right? And then you have this thing called directory entries, which are like inside of a directory you have an inode and a name like pair, and that's what a directory entry is, you know. So like in code you have the name hello.c and then its inode number. Yeah. And so like in in the directory code on disk, all of the entries in code are stored as like the file name and inode pairs. So if we look at like a directory entry, where does that live? Dir entry. Yeah. So you have a name, a size, a type, and an inode number. This isn't actually what's stored on disk. You have a another struct that's a disk directory entry, which doesn't, the actual like type and size is stored in the inode, but this is the in-memory version. So there's a separation between like the disk representation and the in-memory representation. This is the in-memory representation that user space will use. Okay, so when you call open, it needs to like walk this path. So you already have like the root inode is just like slash, right? And so starting there, you need to look for the next like component, which is code. So the way open does this is first you look in the dcache to see if you already have this. I'll talk about that, I guess, later, so I'll skip that for now. But in the if it's not cached, you have to find that inode on disk. So how does that work? Well, starting at the root, you have this inode table that's always in memory. So you can look up the root inode because that's always static. And when you initialize the file system, you create this like cached entry for root as well. So you always have that. So starting there, you get the next path component. So this is a function that just, you know, if we're looking at like code hello.c, it starts here. When you get the next component, it's going to give you code and then step forward to the next one so you can call it again. So it's just a function that lets you like get each subdirectory or component of a path. So for each one of those, you need to try to find that name on disk somewhere. And so since and each time you're in a subdirectory, you know, so you're starting at the root, you know where root lives on disk. So from there, you look through all the names in there and try to find one named code. The other thing that sucks is like the way you have to interact with the disk is via, you can only read a block at a time. And so that's a bit of a pain in the ass. You know, so the way I'm handling it right now is utilizing the arena allocator that I talked about just a minute ago. And, you know, this isn't probably the best way to do it in like a production system, but the way I'm doing it right now is you just read the entire directory entry right away, instead of sort of slowly stepping and doing bit by bit, because we also don't have a lot of other things like IO buffering and like, you know, other things that need to come in the future. So right now we just read the entire thing. And so in order to do that, the first thing you do is get an arena so you can have some memory to store that stuff. You save the position so you can reset it later, and you just you know how big this entry is on disk, so you just allocate enough pages to store all of it. Then you read the whole thing in, and then you start iterating. So the way you do that is this is just raw memory, right? So you kind of have to step forward and like manage like the pointer math yourself. What's up, boss? What you working on? What's up, dude? We're working on a little tiny operating system. Trying to learn how operating system work, so I'm making a little one. Yep. Right now, I'm trying to talk about the things I've done since last time I made a video, and this is talking about how I do like an open syscall. So yeah. So right now we're like trying to find a path. I'm describing how you would like find the like, you know, if you're looking for this file. Right here, how do you do that, right? And so right now, let's say we're starting at root and you're looking for code. So you read the entire directory for like the root slash and look through all the entries in there for code. And if you find it, well, you create a new cache entry for that. And then, you return that inode basically. And if not, well, you failed. But it could live deeper because you found code, right? So you need to find hello. So then you just keep, going through each subdirectory. All right. Conceptually pretty simple, but there's some hairy details about reading disk blocks and stepping forward. And also, you have this notion of like a file offset, and you got to keep that in sync. So there's some gross stuff in there, but that's the basic idea. So if we go back to the caller of this, which was where? Here. Alright, so once you've found that inode, and at this point you will have saved it in the directory entry cache. The other things that happen when you do the open syscall is alright, so on the user space side, you call open and you get back a file descriptor. And so what is that? Well, every process will have a table of file descriptors that is a way to say here's the files that I have open. And that's just like an integer, which is an index into an array that the kernel in kernel memory. So all that user space has is an integer. It's like a handle to that file. But when you open a new when you want to get a new file descriptor, the things that have to happen on the kernel side is, well, first looking in the open file table. So for that file, so you can have multiple file descriptors that point to the same file, right? You can open the same file from either multiple processes or even within the same process. So that's the next things we do is all right, we found this inode, now we need to give the caller of this a new file descriptor. So the first thing you do is find that open file given this inode. So it could already exist, so you look for it. If it doesn't, then you have to create a new one. At this point you will definitely have a file, and what a file is, it's this is the actual information about that file, a pointer to the inode, the cached directory entry for it, a ref count, also the offset. So as you call a read system call, which I'll describe in a second, it goes from that offset, and you have calls like seek, to move that offset around. So it's like a byte offset in the file. Alright, so once you have one of these file pointers, well, now you add a entry in the process's descriptor table that points to that. And actually, this reminds me, there's a good diagram in this book. So the Linux programming interface is useful, has good diagram for this. Thank God I bookmarked it. Alright, here. Hopefully this is clear enough. But this shows the relationship between the user space descriptor table, the system-wide open file table, and the inode table. So yeah, this is a decent book. That's a little bit helpful trying to learn about this stuff. Alright, so the file descriptor table is what maps a descriptor to an open file. And so the file descriptor is just an index into that table. So you've got a new file descriptor now that you can give back to the user space, whoever called the syscall. Okay, that's basically open syscall. So logically, the next thing is reading from a file. So let's look at that. So the read syscall is like this, right? You give it a file descriptor, a buffer to write into, and the size of the buffer. So what does that look like? Well, basically, you need to, given the file descriptor that the caller gives you, make sure that's associated with a file in the open file table. Maybe check permissions if it's like, if it was opened for like read only or not. If it's not like readable or you don't have permissions, then you need to return some kind of error there. But assuming you have a file, you need to start reading from the offset and then update the offset, and copy that out into the user buffer. Buzztronic, what's up? Is this my first time chatting? Yes, it is. Yes, it is. What's up? What's up? Yeah, so how does that look like? Well, file read. Guess you following your offline? Probably. I'm not online very much. Yeah. Alright, so when you read, what's the general idea? Well, yeah, like I said, you have this notion of an offset, like a file offset, and so you just start reading from there. But once again, you have the complication that you can only read from disk in blocks. Yeah, so the approach here is you just see like how many blocks could you read given the size that they're looking for. And then once again, I'm utilizing that arena allocator I talked about, which makes things super simple. It's probably not the best way to do things here, but man, is it convenient. So, we get an arena and just like allocate that many blocks, read all of that in if you can, and then you have to copy it, from kernel space to user space, which in RISC-V you have to like set a bit in the control status register, so you can look at that. Yeah, it's just this. You read the control status register because it can contain like multiple bits of information. So you read it out, then you write in this like S status sum bit, which is what tells you like it sets whether like the kernel is allowed to access like user memory. So it just allows you to from the kernel either read or write to user space memory. So you just have to kind of guard your one like mem copy in between these. So like you set the bit to say, hey, I have access to this memory now, copy it in, and then write the bit back to say, all right, no more access. So yeah, you have to do that copy, and then release the arena, update the file offset, and return how many bytes you've read. That's generally how read syscall works. I'm still missing a bunch of stuff, like I'm not doing the full checks on like permissions and like all of that. So there's still bugs in here and stuff I gotta fix, but the general idea is now in. So that's read. What other stuff did I want to talk about? So, alright, we needed these two syscalls because this is what enables being able to read a directory. So now I think it might be time to look at like how the shell actually does it. So, for example, like for dir. Alright, well, you have to first open a directory. So dir open is basically like the open syscall, but specifically for directories. So let's look at that. Dir open. Okay, so once again, I'm just copying how Linux does things to learn. The way it works there is when you call, mine's called dir open. You give it a path and you get back a pointer to this dir structure, which I think is an opaque pointer on Linux. I don't think you even have access to this stuff, but here you can have it. Basically, they call it a directory stream. It's just a wrapper around a file descriptor with some other metadata. So the way it works is the dir structure has a buffer inside of it, And so, when you open this directory, it's going to open the file, give you, a new file descriptor, write that here, allocate some memory for this buffer, and that's it. And then when you do reader, the way that works is it gives you like the next entry in that directory, but it has buffering, so you don't have to touch the disk each time. So the first time you do a read, it's going to read a bunch of entries into the buffer, and then on subsequent calls to read, it just, while you still have entries in the buffer, it gives you the next one and updates the position. That's the general idea. So you can see here on open, we, call syscall open, allocate a new buffer, and that's basically it. Then on calls to read, which gives you the next entry, what you do is check, have I run out of buffer space? In which case you need to call out to the operating system again and get more entries to fill the buffer. So the way that works, before that, if you already, have buffered entries, you just get the next one and increment the buff position. But in the case that you don't, you have to call out to the operating system. So there's a new syscall called syscall dir entries. I think on Linux it's called like get dents. Is that what it's called? I don't know, let's jump into Linux and see. Get dents, I think. Yes. Yep. So let's look at that. Syscall dir entries. So the interface for this is you give a file descriptor, which must be a directory, a buffer, and a size. And so, a directory entry is has a static size. So given this buff size, you can figure out how many directory entries you can fit in there. Yeah, so this works kind of similarly to like how the OpenSys call has to walk the path, by subdirectory, to find, what you're looking for. This is a similar thing. It's like you give it a directory and it's just listing its, this is like one step of that, basically. So let's look at that. So I do the same thing. I just, use an arena allocator to read basically the entire entry at once. Well, that's not true here. Here we actually, when you're doing an OpenSys call, I read directories entirely at once. Here you have to keep in mind the size of the buffer that they've given you. So however large the buffer that the caller has given, you figure out how many entries you could fit in there. And once again, this is unfortunate. There's a difference between a directory entry in memory and a directory entry that lives on disk. And so the one that lives on disk isn't static size. It stores the name, however long the name is, with some possible padding. It's that. Like on memory, every one is like a buffer of path max size, which is convenient. But on disk, it's variable sized entries, plus they have less information than a dir entry does, so you can't cleanly map them. So you need first a buffer for the disk entries that you're going to read in. So you allocate that, and then you need a buffer of in-memory directory entries that you're actually going to give back to the user. So you allocate that as well. And so you have to keep in mind where you currently are in the file. So you have a current file offset. And from wherever that is, you start reading the next entries. Yep, so you do that, and we also cache entries as we go. So I will talk about the decache, I guess, after this in a little bit. But for now, it's enough to know that we just cache entries as we go, so that further operations in the future that need to access entries don't have to go to disk. And so yeah, you just walk through, get all the entries that will fit into that buffer, and then once again you have to do the like copy into user space, guarded with those like writes to the control status register. And then if you've reached, if you've read all the entries that are in there, we return 0. So the way like the syscall works is it, in the general case, returns the number of bytes that were read. If you've reached the end, it returns 0, and if there's an error, it returns negative value and sets error no. Okay, so that's generally how dir entries works, and that's what enables this dir read function to, have that like iterate one by one that the like user gets to use. So once again, it just fills a buffer with a bunch of entries, and then on subsequent calls, it steps forward if you have one, or refills the buffer by using a syscall to dir entries if it needs to. Okay. Alright, so what else do we want to talk about? I guess we could talk about the Dcache, because that's super useful here as well. And that's also what enables like having like a working directory, which is important to know. Okay, so let's talk about the Dcache. The way the Dcache works is it caches directory entries, the in-memory version. So that's just a basically inode and a name pair. We also store like the type of file and the size. The way that works is the Dcache is basically a hash table. Do I have any? I didn't draw anything for this, but you have a hash table that's hashed, like it's keyed on a like parent entry and the name. So you can see here, that's the hash. So, you always have the root inode, which is just slash. And so it has, we can even look at like Filesystem init. Whoops. Here. So when we initialize the file system, we create a Dcache entry for the root. So the root inode is, the root inode number is known, so you can always look up in the inode table for that and have a valid inode. So given the root inode, there is no parent of root, and its path is slash. And so, on Filesystem init, we create the first entry in the Dcache, which hashes the parent, which in this case is null, which is an interesting thing because like when you do the hashing function, you don't really get good mixing with 0 because like, anyway, I don't know how important that is right now. But it doesn't actually matter because like root is the only one that can have a null inode. Yeah. So like you're not gonna get a bunch of collision because of that. It should be fine. But point being is that just trying to organize my thoughts on this. It's kind of hard to describe like why you key it on parent and name. Like, because basically what you need to know is like the directory it lives in and what's its name. And so that's how you find it. And like, since you always have root, you can start on root and look for like the next subpath, right? Because that's how lookup works. You know, you start at the root, you look for the next subcomponent. So if you're looking for like /code/hello.c, you start in the root, you look for code in there. And so it's very quick. You just hash the parent and the new name, look up in the hash table for that. You know, and okay, so how does this hash table work? The way this one works is the super simple, like you have a certain amount of buckets, and then each bucket you have a linked list in there. So yeah, let's look. So like when you create, when you put a new entry in the cache, how does that work? Well, like we saw in the file system init, like you create this new entry, and then when you put it in the hash table, it hashes the parent and the name, does that mod the number of buckets you have to find which bucket it's going to go into. If there's already entries in that bucket, you just walk through that chain by stepping through the linked list and add it to the end of the chain. You know, ideally you don't have long chains or any chains at all. You can hit an empty bucket, but this is a just dead simple hash table. Yeah, so another interesting thing is like, how does lookup work? Well, that's what I was talking about, where you have like a full path that you're looking for, and you start at the root, and you just do this path next component thing, where you get the next component, and given the parent and that name, you can do hash table lookup on that. If you found it, you set the parent to that one, and then you look at the next name, and you just keep stepping like that. Yeah, so that's like basically the dcache. And so whenever you're doing like an OpenSys call, or you do like read dir, whenever you're reading directory entries basically from disk, you want to cache those. You don't have to hit disk next time. That's the idea. Okay, so that's the dcache. That's the hash table implementation. What else can we talk about? I guess the notion of a working directory as well. So let's look at a process. Alright, so this is like a kernel data structure for every process. One of the things you store in there is the working directory. So initially I had this as an inode, and that introduced problems because there's no way to really map an inode to its path. That's what you need these like dcat directory entries for. So it's changed to dcache entry, which is working now. So the working directory for a process is expressed as this dcache entry. So right now, the way I'm doing it is just like a process starts at root. What I need to do is like, when you're in the shell, wherever that directory is, when you spawn a new process, that will become the working directory. But for now, we only have one process, which is the shell, and its working directory is root. And so the kernel. So that enables this like current working directory system call as well, because a process doesn't have access to its like own process metadata. So you have a syscall, which I call like cwd, current working directory. And so, for example, in the shell, you have like print working directory command. That just makes a call to the current working directory syscall. You give it a buffer to write into, and it writes the current working directory. So the way that works is similar to like this very common pattern where you like walk the path to build up the name. So this one's a little bit interesting because you have to do it kind of in reverse, right? So your working directory is gonna be like, let's say you're inside of like documents, code, just there, right? Like some file. You're in here, right? Well, your working directory is like slash documents slash code. So in here, if you need to find like you want the path, is what you're trying to get. All you have right now is a directory entry, which is like the directory entry for the parent, which is slash documents, and then the name code. So you, given this directory entry, you need to like walk up the parent tree, finding all of like the parents' names and building up a path from there. So like you're starting with code, and then you add in documents, and then you're at the root, right? And so you have to like build it in reverse, and then reverse that path to get the actual path. Yeah, so that's a little interesting detail of getting the working directory. So I just have this path reverse function which allows you to do that, you know. And once again, you have to like do the guarded copy to user space. Us getting a current working directory. And so the next thing I want to do is be able to change directories, which we don't have yet. So I think finally I can try to start writing some new code. Sick. Alright, I think I talked about like all the stuff I need to, so when I post this video later in like 2 years when I don't remember what the fuck I'm doing, I can go back and find it. Thank you, Pass Shaw. Alright, so now let's maybe try to do like a CD command in the shell. Alright, so in the shell, right now this does nothing, it just prints the command. What we're gonna have to do is so the first argument is gonna be the path. So what you need to do is basically check if it's like a absolute path, you're gonna change to that directory. If it's a relative path, you want to use the current working directory to build the full path. For now, let's just think of the case where it's like a absolute path. So let's see. We could do what Windows does. If you call CD with no argument, it just prints the working directory. I don't know. So let's see. If command args len is 0, I guess we can kill that. I guess we can just call current working directory, right? We can call that with the command because it doesn't use it anyway. Sure. Alright. Otherwise, well, we need to call a syscall, so we need to create that syscall. In Linux, I think it's called like chdir. Should we do that, or should we just call it syscall cd, or change dir, or change dir? I guess we can use Linux notation for it. Alright, so you're gonna have a wrapper for it. So like rc change directory command args item 0. Uh-huh. Yeah, so if it fails, I don't know. Do this. The other thing we don't have yet is like a stir error. We just have like a enum for error types. We need to create like a function that maps those to strings. But for now we don't have that, so I'm just gonna say like, hey, we couldn't change to this directory. Okay, but if we could, well, then it'll change. Do we want to like print the new thing? How does this work? No, it doesn't really print it. The prompt just changes, I guess. So that's something to think about. I don't think... Yeah, that's interesting. So our prompt is just like an arrow, but we can maybe have like the directory in there. But anyway, let's do this system call. So we need a wrapper for it. So in user space, we need a chdir, which takes a path. Just do one of these. So, yeah. Oops. I don't know. None of these other ones do I enforce that it's path max, even though like on the kernel side, this is always support, right? It's this path max thing, so I don't know. I maybe should do that, but we'll just write it like that. Okay, so alright, this is just a wrapper for the system call, which is change dir. This is the path, and then just 0, 0. How many arguments are there? 1, 2, 3, 1, 2, 3. Okay. So, in common, we need a new... Oh, we already made that. Interesting. So I was already thinking about that. Kernel. So in here, when we do syscalls, we need one for changing the directory. Alright, so path. Interesting. So if we want to read this, we have to map it into user or to kernel space first. We do. Which is this like interesting. So, you know, I have this copy to from user space function which enables that, but there's a different thing I do and it's a path. Because I have these path helpers that like normalize the path so that it always like doesn't have a trailing slash and stuff like that. So maybe I should make a version of like copy to from that's like specifically for paths. Could do that. Like path copy to from user space. So it has these. And then you would need a size. So in here what you do is like what you do here, which is just this basically. Yeah, we just path copy into path source. Yeah, so let's use that instead. So in here, we can create this path and then do path copy to from user space into path from user path like that. And now we don't really need the comment because it's like, duh, we're doing that. The function tells us that. Okay, and then in here, we do the same thing. This is like user path. Then we have a path here. Path copy to from path user path. I guess we can just do this. Shader path. Alright. This call, shader path. The fuck? Alright, so in here, I guess it's in here where you need to figure out if you're like a relative path going off of working directory. I'm getting a call, but shit. I'll call him back in a second. Okay. For now, let's assume it's like an absolute path. So what do we need to do, right? Well, we need to like find path, like find the next working directory. Because it's like you need to. This could be cached or not. So like you can try walking through like the decache for it. And if you have it, great, you can use that, update the working directory. If not, you need to go out to disk and like try to find it there. So I guess this is like the same thing as like the OpenSys call. Let's just do that over here. Yeah, it's just this, basically. What the fuck? So, sure, we can maybe do the same thing here. So try to find this path in the decache. Also, let's see, to do handle relative paths. So look it up. If it's cached, great, we found the inode for it. Otherwise, we gotta find it on disk. Okay. I guess we're doing the same thing. Like all this stuff is the same, except we're not adding. It's just like the processing of the thing that is not. So. Results. We'll do with that because you're not getting a file descriptor. Alright, try to find an inode on disk. If you can't find it, or okay, if you did find it, so what you actually want here is like, if you have an inode and its type is directory, then we can proceed. But I guess the reason I did it that way is for different error types, right? So it's like if it's not a directory, that's the error we get back. You can't change it into a thing that's not a directory. Okay. Otherwise, what do we do? Well, we need, at this point, we for sure should have a directory entry. So it's kind of like this. So you should for sure have it here. The question I have now is, when you make a system call to change directory, does that open that file? Like, do you create a new file descriptor for that and add that to the process's like descriptor table? Or do you just make a directory entry for that without making a new... I don't think you necessarily have to... let's start with no, and maybe that'll be wrong. We'll see. Why are you complaining? What do you not like? It's this. What's your problem? Why are you freaking out? Oh, that's stupid. Okay. Uh-huh. So right, like this find inode on disk should cache all the entries, so by the time you hit here, you should be able to do this lookup, but I suppose it could fail for some reason. So if at this point you don't have an entry, I don't know, that's an error, so we return some kind of error. What do we have? We have like... no entry, I guess? Okay. Sure. At this point, you for sure have a new entry, so you can say current proc working directory is now this D entry. And your result is 0. Indicating success. Does that make any sense? I think it does make sense. Okay. Sure. Let's see if we have any compilers. We do. Oh yeah, because we're just doing that in... If you want this to know about this, it needs to be here. Incomplete type void. Right, path copy to from user space. This is gonna have actual buffers. Unused parameter. Best. Okay. Well, moment of truth. Is this readable? I don't know how tiny this is. That's fucking huge, but it's probably good for you guys. Alright. Well, what's our working directory? It's slash. What do we have in here? These are what we have in here. So, let's see if we can change to the code directory. Well, first of all, let's just see cd with nothing. Yeah, so this is our current directory. What if we want to go to /code? Okay, now our working directory is code. Boom, that's fucking cool as fuck. We just implemented a change directory system call. Cool. Interestingly, I wonder if this can handle already, like, going back. What if we do that? No. Well, actually, that's bizarre. Interesting. We're in the right directory now, but it thinks we're in, like, /. That's kind of funny. So if we go here, now it thinks we're in /. Okay. So it's correct. It's just, we don't need to, like, if we go into, like, dot or dot, we don't need to, like, add that to the path. But it does functionally work. So what else do we have in here? So if we go into documents, that one didn't work, did it? Great. It says our working directory is documents, but we're printing out the root. I think I know what's wrong. I think when we do the dir command, we're starting at root rather than starting at the working directory. Yeah. Yep. So let's fix that. So let's see when we do, hold on. Dir, what do we do? Dir open, dir read. Path is dot in that case, right? Wait, hold on. So yeah, when you're just dir with no arguments, the path is dot. So that's the path you see on, I guess dir open. Which makes a syscall with dot. Okay. So you're gonna do a dcache lookup for dot, which is this directory. So I think we just need to have special handling for dot and dot dot. This should handle it anyway, because like when we do this finite it on disk, it's gonna walk those. We do have directory entries for those. So it should actually give you back. Yeah, how do we want to handle it? I suppose you do want to actually keep entries for that. You don't want to just like always erase the dot and dot dot and just give back the D entry for the, you know, non-dotted version of it. So, what is happening when we open dot though? So you should have an open file to that. So when you do like dir entries, what's happening there? So you look up the file in the file descriptor and reading from that. I guess the problem is like, so we're in here. If we do dir here, we get that. If we go into code, it's this, but we're still getting the root. So our working directory's right, but the dir call. It's not, it doesn't know about that, right? Oh, wait. So dir entries. Where do we start the search? Where do we do open again? Right. So if this is the path. Yeah. Okay, so right here. The path coming from user space is dot. We're just looking up dot, right? That's based on the root. Here we need to like build up the path using the current working directory. Yeah, so how do we want to do that? So which cases is that? So if it doesn't start with a slash, then it's relative. Is that true? Yeah. Okay, so if path. If it doesn't start with a slash, could path be null here? I don't know. I mean, we're doing lookups and stuff, so we might have to check for that later, but we'll just assume you have a path right now. If it doesn't start with that, it's relative. So what do we want to do? Do we have... This is for sure a kernel buff by now, right? Who calls this? Or when we call this? Yes, so we for sure can access this. So if it's relative, we need to like start with the working directory and build up the name. So you have to build up a path from the working directory and then append this on. So we've already done that before. We might have to like factor that out. So when we do path reverse, that's in here. So current working directory. That literally is what we want to do. So we should just have a wrapper for like a function, I guess, that does it so the kernel can use it too. So how do we want to do that? So we do this. I'm just wondering, do we want to deal with the like return code mode and the kernel mode version of it, or have a different like interface from there? Because you know the easy thing to do is just add a like, is this a user buff? And then the kernel can call it without, and then you don't have to copy out. I think we do it like this. Let's copy this and say get current working directory. This is like a out have max. Usually for process specific things, I append it like this. So like proc current working directory. So, alright, you have this. If you have one of those, we shouldn't really have to do this anymore. Or actually we do, because this is the reversed one. This is the reversed one. We build up the path. This one we don't need. We're just gonna, you know, do this. So we don't do that. Yeah, we don't copy out. Alright, so the error handling of this isn't quite right, but for now this is fine. So we'll just do this. In here, we'll do allocate one of these guys, then call proc current working directory. with this path. Then you say if it's a success, at that point we can do this, I guess. Mm-hmm. And then just return the return code. Alright. Which means we should be able to do that. So that's bad because, like, we're just going to be printing every time. We should do error codes, but for now this will work. So now what we can do is, if it's a relative path, we need a new buffer. What do we call it? What do we call it? What do we call it? I don't know right now. Call it buffer. So you have one of these, and then you're gonna call like proc current working directory with this buffer. I guess you're gonna have to do this. For now, just print some error. That's like error. Like relative path specified. But failed to get process working directory. I mean, this is all development errors for me. Should be changed in the future, but alright, if that's the case, then, you know, at this point we should have a relative path for that current directory. So we can do is like path join. How does this work again? It puts it in path. Yeah. So I might have to copy. So like you need another buffer, so like because we need to join this one to this one. Oh, so that's fine. So we join, this is the current working directory. We join in the relative path. And so now the full path is in buff. But this variable doesn't exist out here, so this is the case when it's like that. So it's like we want to overwrite path, kind of. So what we could do is this. Actually, and do we know at this point that it is? So for syscall open, at this point we know we have one of these now. So we could do this. Relative path is this. We copy into rel path this path. Okay, so now we have a relative path. And then now we use this path as the buffer. So we get the current working directory into path. And then we join into the path the relative path. So, alright, now whether you are a relative path or an absolute path, the entire path string is here. Which means this should work now, right? Let's just see this. Full path is this path. So when we do a yeah. Does it compile? It doesn't. What do we got? We don't have a size. We don't need this anyway, so whatever. Undeclared in 876. We don't know about this yet. Where does this live? What's the problem here? Ah, okay, we fucked this up. Semicolons. Alright, we run. We don't have any errors? Let's make sure. Alright, let's see. So, we do dir. This should print a relative path, right? The full path is slash dot. That's funny. It's pretty funny. Because if we do dir slash, it's not. But dir, it is. Now if we want to go into code, now the full path is slash code slash dot. Alright, we fixed it. So now we're in here. We're in code. We do dir. It's this. Can we go back now? Now we're in here. If we go to documents, and then what's in there? This. Can we do relative now? Can we go into notes? No, because we still don't handle relative there, but we can do documents, notes. So now we're in here, and there's one file in here. Okay. That's pretty cool. That's pretty cool. That's pretty cool. So we can kill that. Yeah, now we need to handle relative paths for what? Where's the other place where we need that? Because, like CD notes doesn't work. Oh, change directory? Handle relative paths. So, let's just use the same, approach. It's basically this. So should this be a function, like get relative path? Probably. I mean, I have to think about how we want to do that, but yes. In this case, we just do this. So this we're going to say is a relative path. We do all that. Alright, so in here, now we should be able to say, alright, we're here, these are that's in here. Let's go into documents. Now we're in slash documents. Going to notes. Nice. We back out. We back out. Sick. Alright. That's so cool. Ugh. We can fucking navigate directories now. Celebration. That might be a good place to stop. Oh shit, how did I just put that up to drink, or has it been muted for like a long ass time? Alright, I sincerely hope that I haven't been muted for forever. But we now have change directory system call. We can navigate a file system, which is sick as fuck. So I'm gonna stop now because I have to make a call and some other stuff, so I'm gonna bail. Yeah, that's it. Peace.